Let's talk a bit about series and sequence. These are two different things, but they're related to one another. If I say sequence, what that's referring to is a list of numbers, something like 1, 2, 3, 4, 5, and sometimes they're grouped in a bracket that looks something like this. A series is very similar to that, and we can say it's those same numbers, except instead of just listing them, we're going to add them together. So 1 plus 2 plus 3 plus 4 plus 5, that is a series. So it's important to know which one is which, right? It's important to know what we're talking about, okay? Now with that in mind, there are two types of series or sequences. The first one we're going to talk about is arithmetic. So arithmetic. And you might see this word and you might want to pronounce it arithmetic, and you can, but it depends on the context surrounding it. In this context, as we talk about series and sequence, we say the word arithmetic because it's describing the type of sequence that we have, okay? So when it comes to an arithmetic sequence, an example of that would be something like 1, 4, 7, 10. And the reason this is an arithmetic sequence is because we're adding the same number each time to get to the next number, right? We keep adding 3. So because you simply add a number to each term to get the next, that makes this an arithmetic sequence. So what can we do with this? How can we define this maybe in some different ways? One way to describe the sequence would be to use what we call the explicit notation. So let me write this down. Explicit notation. Okay, and what that looks like is you have a bracket like this, and we say up here A with a little subscript of K, meaning that's the kth term, right? From K is equal to 1 to 4. And the reason I'm saying 1 to 4 is that in this example we have 4 terms. Okay? With that, we would also state that A subscript K, like that, is equal to 1 plus 3 times K minus 1. Let's think about why I wrote this for a second. 1, because 1 is the first term that we have in the sequence, and then plus 3, because 3 is the term you add each time, and then K minus 1, because that tells you how many times you should add the 3. So for example, if we're talking about the first term, K represents the number of the term. So if you wanted to find A1, for example, A1, the first term, you plug in 1 for K. So you'd have 1 plus 3 times 1 minus 1. Well, we know 1 minus 1 is 0, so this would just go away and you'd be left with 1. So the first term is 1. Well, what if you want to find A2, the second term? Well, then you would say 1 plus 3 times 2 minus 1, because now you're looking for the second term. 2 minus 1 is 1. 3 times 1 is 3, so we're adding 3 just one time. And 3 plus 1 is going to be 4. And of course, the second term is 4. So for this explicit notation, all you have to do is say, all right, we're going from 1 to 4 because we have 4 terms. So 4 is the maximum K you can plug in. You can't plug in 5 because there's no 5th term here, right? This is defined just for these 4 terms. Although you could have sequences that are longer, right, with more terms in them. But for this one, we just have 4. And then this here is the formula to get any term in the equation. So if you want the 3rd term, you plug in 3 for K. If you plug in 4, you get the 4th term. Right? And that's all there is to it. So this is what we call the explicit notation. Now if you want a nice formula based on this explicit notation that will allow you to find any term in the sequence, it would be this formula here. A(n), so the nth term, so any term you want to find, is equal to A1, being the first term, plus n minus 1 times d. That's the same formula as this, it's just written more generally, right? So I would say this is the formula to memorize, or note down at least, right? Write that down. That's the formula to have if you want to find any term in a sequence. So if you have a very big sequence and you don't know, what the 50th number is, but you want to figure it out, and you can recognize the pattern, right? You can see what the first term is, you can see what the d value is, so d being the number you add each time to get the next number. You plug those into this equation, you plug in 50 for n, and that would give you the 50th term in the sequence. So this is an important one to remember. Now, that was the explicit notation. We also have what we call the implicit. also known as the recursive notation. And this one has its uses, although a lot of people don't find it to be as useful. So what you would say here is you'd have a bracket, you say a1 is equal to 1, and you'd say ak, so the kth term, is equal to a k minus 1. That means the term before a to the k, plus 3. So you can kind of see how this works, right? So if you want to find any term, you plug in the term before it and then add 3. Well, that seems kind of obvious, right? Like we kind of knew that's how it worked, right? If you want to find a term in the series and every term you just add 3 to get the next, then to find a particular term, you just have to know the previous term and then add 3. But that's not always a great thing because if we don't know a particular term, odds are we don't know the term right before. So while this has its uses, it's not as practical as the previous formula, right? Either using explicit notation or that formula that I gave you here, right? This is much more useful because it allows you to find any term in the sequence without knowing the terms that are, right before it. So I would recommend memorizing this formula, but implicit or the recursive notation is also good to know. Now, with all this said, those formulas are all good to help you figure out what a particular term is. But what if I want to figure out what the sum of a sequence is? Or in other words, if you turn that sequence into a series and we add all the terms together, and I say, what's the sum of that sequence? How would we figure that out? Well, we actually have an equation for that. It's Sn, so sum of n terms is equal to n, which is the number of terms that we have in the sequence, multiplied by a1 plus an, meaning the first term and the nth term, or the last term, divided by 2. Now, if you look closely, you can kind of see what's going on here, right? If you wanted to find the sum of all the terms added up, all you do is you add the first and last term, divide them by 2. That means you're taking the average, right? So if you take the average of the first and last term, because all the numbers are evenly spaced out, that gives you the average of all the terms. Then you multiply that by how many terms you have, and that gives you the sum. So this is a pretty clever way of figuring out what the sum of a series is, right? So this is a formula that you can keep and that you can remember. So this works for all arithmetic series if you want to figure out what the sum of that is. Okay. Another way to write this is Sn equals n over 2. So that's your n and 2 accounted for. But then in the bracket, what we have is 2a1 plus n minus 1 times d. And the reason this looks a little bit different than this is because this uses that formula that I showed you before to find the nth term, right? And so in this case, if you didn't know what the last term was, it takes that formula, and so you don't have to do it separately. It plugs that formula into this. So if you have a particular series and you want to find the sum, you just plug in the number of terms for n, put it there and here, and then you plug in your d value, which is the number that your terms increase by each time, right? And then you plug in your first term, and this takes care of it all for you. So you don't actually have to find the last term, right? You don't have to find that the way you do up here. You got to find the last term. You just have to plug in the first term, the n, and the d, and it calculates it for you. So that's another important one to remember. So I'd say remember both of those equations. So that was all for the arithmetic sequence, but I told you that there were two. The second one is called the geometric sequence. And the geometric sequence works a little bit differently. I'll give you an example of one. So something like 1, 2, 4, 8. And in this example, I'll just let it keep going, right? I'm not going to say when it stops, but you can see the pattern here, right? Each time you're going to multiply by 2 to get the next term. So in an arithmetic sequence, you add a particular number. In a geometric sequence, you're multiplying by a particular number to get the next term. And just like with an arithmetic sequence, we can come up with some notations to describe this, right? So we have our explicit notation. All you have to say is an, so your nth term, is equal to k times r to the exponent n minus 1. Now I'm going to tell you what each of these terms means. So n is just which term you're trying to find. So if you're trying to find the first term, you plug in 1 for n. right there and there. Right, so if you try to find the first term, n is just 1. If you want to find the second term, you plug in 2, and so on. Your r value here, your r value represents the common ratio. Common ratio. In other words, the number that you're multiplying each time, right? This times 2. 2 would be your common ratio for this example. And then your k value represents the first term. So if you ever need to find the nth term, so someone says, hey, find the 30th term, you plug in 30 for n, you know your common ratio is 2, at least for this example. You know your first term is 1 for this example. You plug that in, and you can calculate the 30th term, or really any term that you want. And so the way I like to write this formula out would be a subscript n, so the nth term is equal to a1, that's the first term, times r to the n minus 1. So the exact same formula as this, but sometimes you see, different variables used to represent the same thing. So this is the version that I like to remember because I know what a1 is, right? It's the first term, and an is the nth term. So I like to remember this version of the equation. Now we also have the implicit or recursive notation. Okay, and that's going to look something like this, where you say a1, your first term, is equal to k, and then you say an, your nth term, is equal to an minus 1. That's the term before an, right, because an minus 1, multiplied by r. So just like the implicit or the recursive notation of an arithmetic sequence or series, we have the same issue here, where to find the nth term, you need to know the term right before it, right? And so this relationship makes sense, right? Of course, the term before the one you're looking for, you just multiply by that common ratio to get the next term, right? That's how the pattern works. You keep multiplying by that r value. And so for the implicit notation here, this isn't really useful unless you know the previous term. So it's good to remember, just like, I'll say the same thing as I said for arithmetic. It's good to know about because it's the most general way to describe, what's going on, and it's the most, I think, common sense way of thinking about it. But it's not really useful for finding any term in the sequence if you aren't familiar with what the previous term is, which you usually are not. That's why I say remember this equation instead. I think it's a lot more practical. Now, with all that being said, we also have some summation or sum formulas if you wanted to add these up in a series, the same way we did for arithmetic. Okay, so these are for a geometric series. So if you have the sum of n, so the sum of n terms, so if you want to find the sum of the first 10 terms, this would be S10. That's equal to a1, 1 minus r to the exponent n, divided by 1 minus r. So deriving this is a little bit more complicated than it was for arithmetic, where we just took the average of the first and last terms, right? So if you want to see how we derive this, I'm going to have a video on that as well that you can check out. But for now, just, remember this formula here. And we also have an equation for an infinite series. Now, in the arithmetic example that I did at the beginning of the video, we had 4 terms, right? And for geometric, you could also have a particular number of terms, right? It could go maybe just 5 terms or 10 terms or whatever. But it's also possible for geometric to have an infinite amount of terms. And while the same is true for arithmetic, if you think of an arithmetic series, 1, 2, 3, 4, 5, 6, if that goes on forever, you can't take the sum. You can't add them up, right? Because it's just going to be growing forever. So that's why for arithmetic, you only have the sum formula for a particular amount of terms. But for geometric, we have an equation for a particular amount of terms and for an infinite amount of terms. Why might that be the case? Because if you think of a geometric example like 1, 2, 4, 8, where it keeps doubling, well, you can't add those together because it's growing, right? It's getting bigger and bigger and bigger and bigger. So if it goes to infinity, you'll never be able to add those together. But you will be able to add them together if that r value that you're multiplying isn't a number like 2 or 3 or anything like that, but if it's less than 1. Okay, let me show you what I mean. So for this equation, it's going to equal a divided by 1 minus r. Okay, r being that number you multiply by each time. This only works if the absolute value of r, meaning that the positive of whatever r is, so it could be negative a half or positive a half, doesn't matter, but that has to be less than 1. So it has to be some fraction less than 1. In other words, r has to be in between negative 1 and positive 1. That's what this means. Now if this is true, then what's going to happen is you will actually be able to take the sum of an infinite amount of numbers added together. You will be able to get the sum of that, which is really interesting. And when that happens, what we say is it converges. So let me give you an example of this. Let's say we have 1, and then the next number will be a half, and the next number will be a quarter. Let me stop here. What's happening, right? Well, each time you're multiplying by a half, right? To get to here, you multiply by a half. If you do that again, it'll get to 1/8. If you do it again, you get to a 16th. And let's say this goes on forever, right? Can you take a guess at what these numbers all add to if you were to add them up? Well, it seems like if you did 1 plus a half plus a quarter plus an eighth, and that just kept going, because you're just adding numbers forever, you would think it goes to infinity. But actually, because these numbers get smaller and smaller and smaller, it's not going to infinity, it's going to converge at a particular number. And if you think about it, 1 plus a half is 1 1/2, plus a quarter is 1 3/4, right? Plus an eighth. You just start adding these really little numbers. It seems like you're just getting slightly bigger than 1 3/4, and really that is what's happening, right? You're getting closer and closer to the number of 2, but you're never going to actually pass it, right? And so this is actually going to converge, and it's going to equal 2. If you want to use that formula up here and find the infinite sum, you would say a, which is your first term, right? First term is 1, divided by 1 minus r, 1 minus 1/2, because the number we multiply by each time is 1/2. Well, 1 minus a half is a half. 1 divided by a half is 2. So it converges to 2, just like we suspected here, right? And if you did this manually, if you did 1 plus a half plus a quarter plus an eighth, and you do it on your calculator, and you keep adding numbers, you're going to get very, very close to 2. Now, you'll never reach 2 doing it manually, but if the series goes to infinity, if it truly goes on forever, then that is when it will converge to 2. Now, there's a few other formulas when we talk about geometric series and sequences. There's one in particular that's pretty cool, and it has some practical applications. And this is when we discuss loan payments. So this is just kind of a sneak peek of what's to come in the other videos, so definitely check them out. And it looks something like P equals L times 1 minus R divided by R minus R to the n plus 1. And this happens when you have an R value equal to 1 over 1 plus I. That's how you find R to plug in here. Now, this equation here, this represents the loan payments that you need to make on a particular loan with a particular interest rate. Okay, there's a derivation of this in another video as well, so definitely go and check those out. But that's just a sneak peek of things to come. So the applications of a lot of these formulas will absolutely have to do with things like loans and annuities, mortgages, things like that. So definitely check those out. But for now, just familiarize yourself with these summation formulas, and also the formula to find the nth term in a series, right? For both geometric and for arithmetic, right? You have these ones and this one up here.